Hi everybody, in this video I'm going to solve an example problem involving one-dimensional motion with constant acceleration. In the course of solving this problem we'll be using the concepts of position, displacement, velocity, speed, and acceleration. We're going to need to use our one-dimensional definitions for average velocity and average acceleration respectively. And we're also going to need to use these special case equations for the special case of one-dimensional motion with constant acceleration. Okay, here's the problem. Imagine we have a bicycle traveling in a straight line to the right. Imagine that in a 3-second time interval, this bicycle accelerates with a constant acceleration from an initial velocity of 4 meters per second to the right to a final velocity of 10 meters per second to the right. We're asked to calculate the acceleration and the displacement during this 3-second time interval of constant acceleration. Now, before I do anything, I need to choose a positive x direction. That's because things like displacements, velocities, accelerations are things with directions. And in a one-dimensional problem, we need to indicate directions with a positive sign or a negative sign in respect to some coordinate axis. All right, so I could choose my positive x direction to be to the right, or I could choose my positive x direction to be to the left. I'm going to choose my positive x direction to be to the right in this problem. All right, with that choice of coordinate system, we can now calculate the acceleration. But before we do that, I want to make a general comment about constant quantities. If something is constant, it's necessarily equal to its average value. So, in order to calculate the constant acceleration during this 3-second time interval, I could actually use the formula for average acceleration. So I'm going to take that and put it right here. We can expand this further. In the numerator, I have the change in velocity. That's the final x component of the velocity minus the initial x component of the velocity. In the denominator, I just have the change in time. That's the elapsed time interval of 3 seconds. All right, so let's plug in now using our coordinate system information. So, final and initial correspond to the end and beginning of this 3-second time interval. So the x component of the velocity at the end of this 3-second time interval is 10 meters, well, I have 10 meters per second to the right of velocity. In this coordinate system, that would go in as positive 10 meters per second. Now I have a minus sign here because I'm taking a difference, I'm subtracting. The initial x component of the velocity is 4 meters per second because 4 meters per second to the right in a coordinate system where to the right is the positive x direction would go in as positive 4 meters per second. The delta t, that's the time interval during which this has taken place. That's 3 seconds. And I've got positive 10 minus a positive 4 equals positive 6 divided by positive 3. That's 2. And I've got meters per second minus meters per second. That gives me meters per second divided by seconds. So that gives me meters per second or meters per second squared. All right, so the acceleration during this 3-second time interval is 2 meters per second or 2 meters per second squared. Now let's interpret the sign. This came out positive, so that would mean that the direction of the acceleration is to the right, and that makes sense. It was traveling at 4 meters per second to the right, and then later it's going 10 meters per second to the right, so it's increased velocity to the right. And the acceleration is the rate of change of the velocity. So what this says in words is that during this 3-second time interval, the acceleration, that is the rate of change of the velocity, is 2 meters per second. So every second it picks up 2 meters per second more of rightward velocity. To spell that out even more, it's initially going at 4 meters per second. Then 1 second later, it'll be going at 6 meters per second. Another second later, it'll be going 8 meters per second. And then 1 second after that, it's going 10 meters per second at 2 meters per second for 3 seconds. That takes you from 4 meters per second to 10 meters per second rightward. We could also have used the first of these constant acceleration equations, which says that the x component of the velocity at time t is equal to the x component of the velocity at time 0 plus the constant acceleration times the elapsed time. Let's take that equation, put it right here. Now let's plug in. And again, we're taking to the right as our positive x direction, so all our quantities have to be consistent with that. V sub x 0, that's the x component of the velocity at time 0. Time 0 is at the beginning of this 3-second time interval, so that's positive 4 meters per second. Now, a sub x, that's what we're looking for. T, that's the elapsed time from the beginning of the time interval to the end of the time interval. That'll be 3 seconds. And v sub x, that is the x component of the velocity at this time t, 3 seconds after we started the clock, so 10 meters per second positive. Okay, so we can subtract 4 meters per second from both sides to solve this. 4 meters per second minus 4 meters per second, that'll give you a 0 right here, and this will carry down. 10 meters per second minus 4 meters per second is 6 meters per second. So 6 meters per second equals a sub x times 3 seconds. Divide both sides by 3 seconds. So we'll have on the right-hand side a sub x, and on the left-hand side we'll have 6 meters per second divided by 3 seconds. That'll give us 2 meters per second, or 2 meters per second squared. So the x component of the acceleration is 2 meters per second. Again, in our coordinate system, where the positive x direction is to the right, that means 2 meters per second to the right. And if I want to write this as a vector in magnitude and direction notation, I'd have acceleration vector equals 2 meters per second to the right. All right, so I'm going to box this and I'm going to erase this so that we have room to deal with the displacement part of this problem. So here we go. Now let's find the displacement of the bicycle during this 3-second time interval. Displacement, remember, is change in position. So what this question is asking for is, during this 3-second time interval, how far to the right does this bicycle move? Okay, we're going to do this 3 different ways. The first way, I'm going to use this equation right here from our list of constant acceleration equations. This equation says that the x component of the displacement during some time interval is equal to the initial x component of the velocity multiplied by the time interval plus half the x component of the acceleration during that time interval, which has to be constant for this equation to work, multiplied by the time interval squared. All right, let's take this equation and put it right here so we can use it. All right, here's the equation, and then I've rewritten it below, but with spaces so we can fill in the numbers. All right, so we're looking for the x component of the displacement. We need the x component of the initial velocity. That's the x component of the velocity at the beginning of this 3-second time interval. That's going to be positive 4 meters per second. So I'll plug that in. T, that's the elapsed time for this full time interval that we're looking for. Since I'm trying to find the displacement for a 3-second time interval, I need the full 3 seconds. If I was only going to find the displacement for a 2-second interval, well then I would plug in 2 seconds, but I'm trying to figure out how far to the right the bicycle goes during 3 seconds, so that's what I need there. All right, plus 1/2, I need the x component of the acceleration during this time interval. Well, we already did that. That's 2 meters per second. And then again, I need the elapsed time squared. Again, I need to use the same time here as here because I'm trying to find the displacement that corresponds to this amount of elapsed time. All right, so I want to find the displacement during a full 3-second time interval. I need the full 3 seconds in for the time. All right, so let's work out the parts of this. 4 meters per second times 3 seconds gives me 12 meters, because seconds divided by seconds gives us 1, and then we're left with units of meters. I've got plus here, and now I'm going to have 1/2 times 2, that gives me 1. And then 3 squared, that gives me 9. All right, and let's work out the units. I'm going to have meters divided by seconds squared multiplied by seconds squared. Well, the seconds squared divided by seconds squared, that divides to give 1, and then I'll be left with meters, these meters right here. So I'm going to have 12 meters plus 9 meters, giving me a grand total of 21 meters. Now, let's check our sign. I chose my positive x direction to be to the right. So if I get an answer of 21 meters positive, that means 21 meters to the right. That means the bicycle has moved 21 meters to the right during this 3-second time interval. To the right makes sense. It was heading to the right. There's no way it can go left if it's going to the right and speeding up. Okay, great. One quick comment. If the acceleration had been 0, then I'd have a 0 here. 0 times anything gives me 0, so I'd have nothing right here, and I would have a displacement of 12 meters. Well, that makes sense, because if the acceleration is 0, that means the bicycle would just continue on at 4 meters per second. 4 meters per second for 3 seconds would give us 12 meters. That is, during the first second, it would travel 4 meters. During the second second, it would travel another 4 meters. That's what it means to travel 4 meters per second. And then in the final second, it would travel another 4 meters. 4 meters plus 4 meters plus 4 meters is 12 meters. So that's how far it would go if the acceleration had been 0. The acceleration isn't 0. The acceleration is 2 meters per second, so each second is picking up 2 meters per second worth of velocity, and so therefore it travels further than it would have if it had just continued on at 4 meters per second. One more quick comment before moving on. This equation and this equation are really the same equation. I could take my delta x, my change in x, and write it as x at time t minus x at time 0. I could then add x at time 0 to both sides, so add this to both sides. It'll be gone from this side, and it'll appear on this side, giving us this equation right here. This top form of the equation is really convenient if you're trying to find the x component of the displacement. The bottom form is really convenient if you're given an initial x location and want to find a final x location, or if you're given these locations and you want to find something else. So sometimes this form is more convenient, other times this form is more convenient, but they're really the same equation. The second way I'm going to calculate the displacement is to use this constant acceleration equation right here. This constant acceleration equation can be really useful in situations where you don't have the time. Now in this problem we do have time information, but I'm going to use this equation anyway as a check on our first calculation. So let's take this equation and rewrite it right here, and meanwhile I'll erase some of these other calculations right here. So here we go, boom. In this equation, delta x again is the displacement. A sub x is the x component of the acceleration during that displacement. V sub x0 is the x component of the velocity at the beginning of the displacement, and V sub x is the x component of the velocity at the end of the displacement. All right, so let's figure out what those numbers are and plug them in. Starting left to right. V sub x, that's the x component of the velocity at the end of the displacement. So at the end of the displacement, we've got an x component of the velocity of 10 meters per second. And I've got to square that. V sub x0, that's the x component of the velocity at the beginning of the displacement. That's this 4 meters per second. Then I've got my plus, I've got my 2. A sub x, that's the acceleration, the x component of the acceleration. We already figured that out. That's 2 meters per second. And then delta x is what we're looking for. I'll leave it to you to work out the algebra. We can subtract this from both sides, then divide by this, solve for delta x, and we'll get delta x equals 21 meters just like we calculated here. So the x component of the displacement is 21 meters to the right. This came out positive. That's consistent with our rightward x direction that we chose. The third and final way that I'm going to find the displacement in this problem is through a two-step process. First, I'm going to take the last of these constant acceleration equations to calculate the x component of the average velocity. I'm going to take that, put it up here into the definition of x component of average velocity, and then solve for the x component of the displacement. All right, here we go. First, before I use this, I want to give us some cautions. We can only use this in the case of a constant acceleration. This isn't true in general. This is just true in the case of a constant acceleration. Now, we do have constant acceleration here, so we can use it in this problem. All right, so I'm going to take this, put it right here. Now, v sub x0 is the x component of the velocity at time 0, or at the beginning of the time interval. That's 4 meters per second, so I'll put that in right here. And v sub x is the x component of the velocity at the end of the time interval for which we're calculating the average velocity. That's going to be 10 meters per second. I'll put that in right here. All right, 4 meters per second plus 10 meters per second is 14 meters per second. Half of that will be 7 meters per second. And that'll be the x component of the average velocity. All right, meanwhile, let's take this equation and solve it for x and put it right here. V sub x average, we just calculated, is 7 meters per second. Meanwhile, delta t, that's the elapsed time interval for this process. That was 3 seconds. 7 meters per second times 3 seconds gives us 21 meters in agreement with our other calculations. Finally, I can write the displacement in full-blown vector notation as follows. Delta r vector, that's a nice symbol for the displacement in vector notation. That's magnitude of 21 meters and direction to the right. And that's the displacement vector in full-blown magnitude and direction notation. All right, we've solved the problem. But before signing off, I've got 3 final comments. The first comment relates to our choice of the positive x direction. What would have happened if instead of taking the positive x direction being to the right, what if instead we had taken the positive x direction to be to the left? Well, that would have just changed the signs of some of our numbers. So for example, 4 meters per second to the right and 10 meters per second to the right, well, those would go in as negative numbers if our positive x direction were to the left. If the positive x direction is to the left, then directions to the right would be negative. So the 4 meters per second and the 10 meters per second would have gone into our equations as negative numbers. Also, the acceleration we would have calculated would have come out negative. The acceleration vector is 2 meters per second to the right. But if left was the positive x direction, then in terms of an acceleration component, that would have come out negative. Likewise, if we had chosen the positive x direction to be to the left, then displacements to the right would be displacements in the negative x direction. So a displacement vector of 21 meters to the right would correspond to a delta x of negative 21 meters rather than positive 21 meters. In this connection, I need to emphasize that in these equations, the quantities delta x, v sub x0, a sub x, wherever they appear, they correspond to sign quantities which represent one-dimensional vector components. The sign, positive or negative, indicates directional information relative to the direction of the chosen positive x direction. Second point. I want to emphasize the difference between speed and velocity, and also between distance and displacement. First, speed and velocity. An object's speed at any instant is the magnitude of that object's velocity vector at that same instant. Speed is how fast something is going. Velocity is how fast and in what direction. So, for example, At the end of this 3-second time interval, the bicycle has a speed of 10 meters per second. That's how fast it's going. At the same instant, it has a velocity vector that has a magnitude of 10 meters per second and a direction to the right. Now, in a one-dimensional representation in which we have taken the positive x direction to the right, the representation of that velocity would be positive 10 meters per second. As a number, that's indistinguishable from the value of the speed, which is also 10 meters per second. But conceptually, there's a difference. Speed is always positive, but a one-dimensional velocity component could either be positive or negative. And so that brings us to this. The v's in these equations are not speeds, they're velocity components. They can carry positive or negative signs that correspond to directions of our one-dimensional coordinate system. Now for distance and displacement, and this is a bit more complicated. Displacement is a vector that gives an object's change in position during some time interval. The magnitude of the displacement vector is the length of a straight line drawn from the beginning position to the end position. So in this example with a 3-second time interval, the magnitude of the bicycle's displacement is 21 meters because that's the length of a straight line drawn from this location to this location. The direction of the displacement vector is the direction of an arrow pointing from the beginning position to the end position along that straight line. So in this case, the direction of the displacement vector is to the right. So the displacement vector in this case has a magnitude of 21 meters and a direction to the right. In our one-dimensional representation with a positive x direction chosen to the right, we'd represent that as delta x equals 21 meters, as we did in these various calculations. Okay, now for distance. Distance is the total length along the path actually traveled. Now, in this case, the bicycle went in a straight line without reversals. It ended up 21 meters from where it started. Its length of travel was 21 meters. That's the distance traveled. However, let's imagine another object. Maybe it started here with the bicycle and then ended at this same location that the bicycle did, but maybe it took some other path like that. That other object would have traveled a longer distance than 21 meters because we have to take the full length of that actual path traveled. So this other object, starting at the same location as the bicycle started, ending at the same location that the bicycle ended, it would have a different distance than 21 meters, but the magnitude of its displacement vector would still be 21 meters because displacement is along a straight line regardless of the path traveled, whereas the distance is measured along the path actually traveled. All right, now what about these equations? In these equations, delta x, wherever it appears, represents a displacement component, not a distance. The distance does not appear in these equations, just like the speed. Speed does not appear in these equations. Third and final comment. What if we had been given the same initial velocity information, the same final velocity information, the same 3-second time interval, but we are told instead that the acceleration was not constant? What then? Well, in that case, the most we'd be able to do would be to calculate the average acceleration for that time interval. And we'd get the same answer for that, 2 meters per second to the right. But if the acceleration is not constant, we could not calculate the displacement. We calculated the displacement 3 different ways, but all 3 of those ways involved using equations that assume the acceleration was constant. For example, here, also this equation, the acceleration is not in there, but that's an equation that assumes the acceleration is constant, and likewise here. All 3 of those equations, all these equations require that the acceleration be constant in order to be valid. If the acceleration is not constant, then those equations aren't valid and we can't use them to get a valid result. All right, so if the acceleration had not been constant, we could calculate the average acceleration, but we wouldn't have known how far it went. All right, that's all I've got. Thanks for watching, and I'll see you next time.